All right, so what we covered yesterday was, we looked at some motivating examples, and then we went through some basic ideas regarding testing, and primarily the important concept of multiple comparisons. And then there was a question, or some participants wanted to hear a little bit more about power, so I added some slides, and essentially that's where we were going to start before we switch to multivariate methods and how we look at the data from a broader perspective. So I start with the definition of the power because this is going to provide insights of what issues we address when we look at power analysis, which is needed in many cases, to justify where you're using a particular sample size in a lot of R01 or R21 applications, and what are some of the challenges and what are some issues that you need to be aware of. So the power is, if we go back to to this table, no, actually even further back. Yeah. So if we go back to this table, then the question is, how you control this type of two error, and that's where power starts coming in. So this is not. So power, the way we define it, is the probability of correctly rejecting a false null hypothesis. So for example, if we go back to the Swan case study, one of the null hypotheses that we have, or the most common null hypothesis that you're interested in, is that if you're agnostic, that the mean levels of metabolites are the same, and therefore what you would like, suppose that the mean levels for a particular metabolite were different, then you would like sort of to maximize the probability of correctly rejecting a false null. Because the null, in that case, the null hypothesis always says that the levels are the same. Or in other type of models like ANOVA models, they say that the effect of a factor, let's say, between the two groups is not important. So for example, for Chuck's case, one of the hypotheses that we may have wanted to test was whether there are differences between the controls and the NFLD subjects. So the null says there are no differences. The alternative always says there are differences. So the same is here. The null is always postulates that there are no differences, and that's what we would like sort of to assess the probability that we're correctly rejecting a false null, meaning that for the study under consideration, there are differences. So essentially, another way of thinking about this issue is that the power of a test assesses the probability of detecting true differentials. So the question is, what that might happen, and there are two possibilities. But the null hypothesis is actually true, but the more important in applications perspective comes from the last bullet point. You may not be adequately powered. That's why power analysis becomes important when you design your study. Of course, in many cases, you acquire samples of convenience and you are stuck with a particular sample size. But if that's not the case, and for example, you design the study yourself, that's where power calculations come about. So remember that at the end of the day, if I go back to some of the slides that I showed you, some of these comparisons, it's easier to use. So one issue is that unless your data are very tight, and that's why a lot of questions that came up yesterday when TM presented the lipidomics platform, and that's why you would like sort of to have good RSTDs for the compounds that you're going to study downstream, is how well the variances are controlled. And of course, the variance in your data is also a function of how many samples you have, provided, of course, that the platform has provided good data. So if you have only 5 values, you may have quite a lot of variability just by chance, and therefore the box plots are not going to be fairly tight. And even if there were true differences, your test is not going to be able to detect them because of too much noise. Correct. Because remember, at the end of the day, what enters into the calculation of the test is the estimated standard error, and the standard error is the true variance that you have from the data divided by the sample size. So it goes down as your sample size increases because that sort of tightens the statistics that you use in your test. So, of course, but you may not be able to come up with better estimates of variance because your data, the underlying data, may be truly, truly noisy, and then you're out of luck. Even if you use humongous sample sizes, it's not going to sort of help you. That's why the first step is to really have good data, and then that's where the sample size question comes about. So that's why when, for example, in mouse experiments or in cell line experiments, you expect that the variances are fairly tight, but my recommendation is always have at least 5 replicates. Something can always go bad, and if you have 3 replicates, 1 replicate is bad, and then your variance explodes because you only have 3 data points, and a lot of true differences will not be able to detect them. That's exactly where you lose power in the testing setting. Okay, so back to, oops. So that's where the notion of sample size comes about, because it may be insufficient sort of to really calibrate the standard errors of your data when you use them for testing purposes, and therefore you don't have the right level of detection, and hence you reject the null. And again, remember that when you do all these hypotheses, there are always 2 issues coming up. One of them is how big is the true difference, which essentially you estimate by the means of the metabolite levels in the 2 conditions. If this is humongous, potentially you can afford more noise and still your test is going to have good detection power. But as sort of the difference start becoming more subtle, that's where variance starts kicking in, and that's where you would like to be adequately powered. Otherwise, you may sort of not be able to reject the null, even if the null was false. So, so essentially, the objectives of power analysis is so you can use it in 2 ways. So the first question is, or all these are intricately linked. So if you have already selected the sample size, you already have your data, and therefore your sample size is fixed. There is nothing you can do about that. One way of sort of using the notion of power is sort of to assess that probability that you are able, with what probability you are able to reject the null hypothesis given the sample size that you already have when the null is not true. So for example, if, as you do all these calculations, up to this point we have really talked about p-values and false discovery rates and stuff like that, but somebody may ask, okay, with what is the probability that, given the fact that you have 10 subjects in the control and 5 subjects in the NFLD, you are able to reject the null hypothesis when it is not true. You do the calculations, and you say that test probability is 0.8. That's the power of your test for the given sample size that you have. Hopefully, for the SWAN data, you have much higher power. I'm going to show you some plots on the next slide, because we have about 60 and 60 subjects. So hopefully, the test has higher power. If you start designing a study, of course, then you need sort of to provide some additional information, how big you expect the difference to be. But and that's where power analysis comes when you're trying to figure out what the appropriate sample size is in order to be able to detect certain differences that from previous studies or from the literature, people say that, fold changes or whatever for particular metabolites are, in order to write in your grant and say, I'm adequately powered. So in that case, the free variable is the sample size, and you're trying sort of to detect it, and what you fix is the power of the test. You say, I set my probability of rejecting the null when it is not true at 0.9. So I want 90% power, or I want 80% power, or I want 99% power. And then in order to achieve such power, because if you have power 99%, that gives you much more confidence that essentially you're going to nail all the differentials, or with high probability all the differentials, then that obviously will require a higher sample size. And then that's why you put in the power analysis, all these tables, and say, at 80% power, I need a sample size of 25. So essentially, when you are trying to address the second bullet point, you need to provide some notion of what, you need to have some prior information about the differences. So essentially, in this case, you need to define what the differences you expect to find, for example, fold changes, and this may come from your previous study or from the literature, plus what power, what level of power, what this probability should be, you're comfortable with. If somebody says, I only want power to be 55%, essentially you just want to be doing a little bit better than chance. So, and in that case, essentially, you use a certain machinery, there are formulas out there, and that helps you determine the required sample size. So you see, all these things are intricately linked. In the first bullet point, you already have whatever the differences are already embedded in your data, because you have your data, you have the sample size, there is nothing you can do about those two quantities, and the only thing that you want to calculate and to convey to your audience is what the power of your test is. In the second bullet point, I'm not trying to be too pedantic, but what information you use, you need somehow to say what type of differences you expect and what type of power you would like to achieve, and then essentially the equation that you solve for is in terms of the sample size. Okay, so let's look for one of the metabolites, named metabolites that are in the SWAN study. And in this particular case, the diabetic and healthy group sample size is fixed. We know that, and we're looking at 30 and 60. And the calculated standard error for a slight variant of the vanilla t-test is this quantity. So the null hypothesis says that the equal means between the diabetic and the healthy groups exists for this particular compound, and of course the alternative is that there are differences. So the other thing that obviously comes into your calculations is the type 1 error. So that's another quantity that you need to fix when you do all these calculations. Never forget the type 1 and the type 2 errors. And as we briefly discussed yesterday, there is no way to optimize over 2. One at least needs to be fixed. So in this case, we fix it at the usual 5% level. And then we start looking sort of at this type of curves. Essentially, we sort of summarize what power you would achieve for different type of differences. Okay. So the observed difference is 0.75. So essentially, I'm not having that much power for this particular metabolite, because, for example, when I do this type of calculations, when the true difference is -1, I go back to standard formulas that are implemented in software, the power of the test is 0.73, and you see that as I start getting higher mean differences, the power starts going up. So another way to think about it, since a lot of people in the omics area want to think in terms of fold changes, if you have enormous fold changes, essentially the two hypotheses are very far apart in terms of the mean levels. Or another way to see that is that the box plots don't even overlap when you plot the data, and in that case you achieve a very high power. As the two hypotheses start coming in the data, the two groups, the mean differences start coming closer together, essentially, power starts going down. And at some point, essentially, that's what happens is that, given the sample size that you have, there are not significant shifts to be able to adequately detect the change, given your sample size. Of course, so that's where there is another point that we don't emphasize enough when we cover statistical concepts is the concept of statistical significance versus biological or real significance. What we mean by statistical significance and all these probabilities is that you are able to detect a difference. So for example, if somehow you had a difference of 0.0001 and somehow you're able to generate 1 billion samples, you're still going to be able to detect it. That's the only thing that the statistical test does. Then it's up to you as an investigator to assess whether such a tiny difference has any biological meaning or not. The only thing that the test does, and I've seen that in many papers where people overinterpret the results, the concept of statistical significance, which is potentially a bad terminology, says that something, given the data, the noise levels, and so on and so forth, and all this machinery, you are able to detect it, and you can calculate power and so on and so forth. It doesn't mean that statistical significant results may be biologically significant. The difference may be tiny, and as I told you, if you have very, very large sample sizes, you are able to detect, a lot of things. It doesn't mean that they're really important from the subject matter's perspective. So if some of you get involved with very, very large studies, and right now there are a number of studies in different areas where we are gathering a lot of data, essentially, you need to be cognizant about this issue because, all your tests are going to be able to detect a lot of differences because you're adequately powered. That's exactly what this discussion is about. On the other hand, it doesn't mean that all these results are significant from a scientific perspective, okay? So, and here is the curves that we want to show in grant applications. You fix the type of test, and of course you need to some additional assumptions, whether the two groups have equal sample size or they don't. All these formulas have been worked out almost 70 years ago. You fix the level of the test, and then you specify the effect size. This is what you assume from prior knowledge are the differences between the two groups. And essentially, you get these power curves as a function of the sample size. So for example, if the effect size, the mean change that you're looking at is 0.5, you can see that in order to start achieving really high power and essentially really being able to detect the changes, you need much higher sample size, and this is perfectly consistent with intuition. The two groups are fairly close, and therefore, essentially, you need a much higher sample size to really calibrate the standard errors, in your testing procedure. When the effect size becomes large, that means that the two groups are further apart according to your data. And then with a much smaller sample size, so you see here, we are almost at 95% power, or the probability of detecting that the null is false when it actually is false is almost 0.95. So this is a high probability, and we feel comfortable that we are going to sort of detect all the changes. You only need 30, whereas to achieve the same level of power, if the effect size is much smaller, is 120. So that essentially gives you sort of all the trade-offs. And there are a lot of quantities that go into this type of calculations, or a lot of info. Whether the two groups are equally sized, otherwise some of these curves shift a little bit, but the main effect that if the effect size is weak, even if you had an equal sample size between the two groups, is going to have the same ordering. The stronger the effect size, the power curves moves to the left, and with a smaller sample size, you achieve the same level of power. And of course, you need to set the level of the test. If this was 0.025, all the curves are going to start moving to the right because you become more stringent in terms of a type 1 error. And so there are a number of decisions that you need to make and provide some justification, for example, when you do power analysis in your grant. So what are the take-home messages for power analysis? I've already emphasized the notion of the sample size. And the other things that you need sort of to pre-specify is the level of the test and so forth. And the two questions that you can use the notion of power, as we've already mentioned, is what is the required sample size to achieve the desired level of power, or what the power of the test is given the data that you already have. Where do we go from here? For simple tests like t-tests and other variants, non-parametric tests like rank sum tests, there are many software tools. There are even web-based tools that you plug in some numbers on your web page, and it spits out either the sample size or the power. Again, depends on which quantity you plug in. There are also results in the literature that, so this is important when, for example, in omic studies, you're doing a power analysis for an omic study, whether it's metabolomics, lipidomics, or RNA-seq. All these things are if you do only one test. But remember, when we have this multiple comparisons problem, the alpha levels are affected, and therefore you need sort of to do that adjustments. So by using, for example, software that has been designed for a classical setting where you are only doing one comparison and postulate those results in your grant, a careful reviewer is going to say you haven't done the calculations correctly because you're not only testing for one metabolite, you're testing for 300 metabolites, because that's what you are telling in the grant application that the MRC2 platform is going to detect. So then you need to adjust all your power analysis for FDR corrections. By now, there are papers that have fixed all these calculations for these simple tests. You're not going to find them on web-based tools. You need sort of to power up R, load the right package that implements the methodology. But in that case, by just going to the web, you're going to have their own results, because as far as I've seen, I wanted to do a quick power analysis on the fly for a collaborator, and I went to the web trying to do it in 3 minutes because I was lazy and I didn't want to power up R and start loading packages, and there was nothing there. So for omic studies, you need to take that into consideration because the sample size calculations change and so on and so forth. What about more complex models? Well, there are fewer tools. When we start getting much more specialized, for vanilla ANOVAs, I mean, you're not going to find them on the web, but they're implementing a number of software packages, the same for regression. But the moment you start going even to more fancy ANOVAs where you have, a lot of factors, and the factors may be nested, similar to what we were discussing yesterday for Chuck's PUFA study, then you really need to consult with an expert. Because then all these issues become very subtle of how you do all these calculations, under what assumptions, and then you need sort of to have a really good understanding of what the model says, what are the assumptions of the model, in order to get the right results and put in your grant application. So if you do, for example, a validation study, and essentially you're testing whether sarcosine is an important metabolite for discriminating between prostate and non-prostate patients, and that's your only biomarker, you can find it on the web, so you can do it yourself. But if you're trying to construct or do the power analysis for a biomarker panel, this little annoying thing comes into the picture, and you need to address it carefully. And if you are really going for much more fancy models, that's why people like me have a job. So You know, there are too many subtle issues that, you know, unless you sort of understand exactly where all these issues come from, because you may have also heterogeneity in your data, and all these issues that came up in various presentations yesterday play an important role in order to really have a solid power analysis. Any questions? Because, yes.
Do you remove outliers before do these tests? Or because sometimes it's hard in biological samples to find an outlier?
So the question is, what about outliers? The issue with outliers is, as we saw in that plot, essentially you have the box plot and there is one value up there, inflates the variance and essentially kills the power of the test. Here, actually, so there are two issues with outliers. One of them is if you have an outlier for a single metabolite and you're testing for that metabolite. That's very easy to spot by just doing the box plots and seeing this huge value. And in that case, the simplest thing to do is not to remove that observation because you don't know its profile across all the other metabolites. It just may have, for whatever technical or other reason, for only this metabolite an outlying value. So you don't want to remove a whole sample from your analysis because on all the other metabolites it may have good values and so forth. So in that case, instead, for example, of using the standard mean, there are extensions where you use trim means, which essentially downgrades the influence on the mean value of your metabolite for one of the groups, the influence of such an outlying observation. Or otherwise, you go non-parametric because in non-parametrics, essentially, you are testing the ranks of the data rather than sort of the actual values. On the other hand, and that's a much harder problem, and I'm going to show you one possible technique. What happens if one of your observations has large values or small values across the entire panel of metabolites that you're profiling? This is called the multivariate outlier, and unfortunately, this is much harder to detect. So in that case, if you're able to detect it, and we're going to see how, for example, principal component analysis can be helpful in those cases, then that's a more serious decision because then essentially you throw out one sample from your entire study and that may have particular consequences. Or actually in many cases, that sample may be the most interesting to study. You know, extreme observations or extreme samples, either they may come up because of some technical issue or biologically they may be the most interesting ones, especially if you have, for example, a cluster, a number of those. In that case, actually, you know, my preference will be sort of to zoom in and try to understand why that cluster is so different than everybody else, although they belong to one of your groups under consideration. So if it just comes for, again, summarizing, if it just comes up on a couple of metabolites, you can do technical things without throwing it out, but if it's a consistent outline observations across your entire panel of compounds, then you need to think harder of whether this is a really bad sample or there's something more interesting going on. Other questions? Yes.
If you were submitting a grant with a targeted and untargeted aim, would you do separate power calculations for
Oh, absolutely. Yeah. Because they, you know, from what we have heard from all the presentations, so the targeted platform, first of all, has all these calibration curves, and at the same time, usually you're dealing with a much smaller set of compounds from the assay. So your multiple comparisons, essentially you may be doing 80 multiple comparisons, depends on the size of the assay. The untargeted platform, you know, despite best efforts by the community, still has much higher variability, and also the number of tests that you're going to do is 300, 500, depends on how many features you would like. So, and again, it's how you pitch the grant. So for example, if it's just an initial profiling study and you have no idea, you know, what you're going to sort of find, in that case, potentially you may have to put everything together and say, you know, this is a pure profiling study. I'm trying sort of to discover and come up with interesting hypotheses. If the spin on the grant or the pitch on the grant is, I'm following up on previous literature, and that's why I'm using the previous assay, but I'm also doing the untargeted to find other interesting things, then you need to separate the two power analysis, because with the targeted assay, essentially you're doing a follow-up to things that are already in the literature, and therefore you would like to tell the reviewers, I'm powered enough sort of to really replicate my previous findings or previous findings in the literature, and then you're providing essentially what power you're going to achieve to find new discoveries, because let's say new platforms have better characteristics and so forth. So everything depends on, what the pitch is, what the question you're asking, what the setting is. There is, I know I'm not super helpful, but there are too many variants of, Other questions? Karen.
So with correcting for FDR, do you ever relax the p less than 0.05?
Oh, yes, absolutely. Because, yes. And for those of you that, and again, depends on how clean the data are, but, if we get outside the metabolomics and we start going to GWAS studies and SNP analysis where you have millions of those, obviously you need sort of to relax some of the criteria. And the communities have come up with guidelines. So that's where things that Maureen just emphasized and the efforts of the lab to clean up the platform so that the features that you get are real, so that you don't have fragments and so forth are important, because I have seen data sets from other cores where they don't go through that exercise and then suddenly they dump 4,000 spectra or 4,000 features. And if you take them all for granted, then, you're doing too many multiple comparisons, whereas some of them may provably be junk. So that's why sort of cleaning the features is a very important part of the exercise, and that's why you need sort of to ask those questions when you shop for a core to run your analysis, or for a company for that matter. Other questions? All right. So right now we're switching gears and we start going a little bit more higher up in the analysis. Essentially, here we're trying to take a global view, a more holistic view of all the data. We had a number of presentations where, you show a PCA plot. Probably all of you have used principal component analysis, either doing your study or reviewing a paper or reading a paper, and also cluster analysis. So let's understand what principal component is about. Essentially, as you have this data cloud, your samples living in 300-dimensional space because you have 300 metabolites, essentially the principal component analysis is trying sort of to identify, as a function of your metabolites, the directions of maximum variability. So essentially, if I had a football, my data lived in a football in this 3-dimensional room, this direction is the principal axis for this football because that's where I have maximum variability. And therefore, somehow, I have 3 metabolites, X, Y, and Z, and therefore I'm trying to essentially to solve for an equation that is a weighted combination of these 3 metabolites that characterizes this line. Why am I saying this? Well, because there are thousands of papers in the literature that use PCA to do cluster analysis, and on many occasions it works well, but it's not the right technique if you really want to cluster your data. Because the technique, what it's trying is to essentially summarize the data from this perspective, where there is most variability in the data, because you believe that that's where a lot of interesting things happen. And essentially, it leverages the correlation structure, because, for example, if I didn't have a football where sort of one of the axes is more elongated, which means that the underlying correlation structure is stronger because the variables start getting correlated, but I had a soccer ball, essentially you have uncorrelated data, then principal component analysis is not going to be that useful because essentially the direction of maximum variability is undefined. If you have a soccer ball, all directions are of maximum variability and of equal variability. So in that case, PCA is essentially semi-useless. So, or actually totally useless. So the directions of maximum variance, not maximum variable, maximum variance, are determined by these combinations, linear combinations. So essentially, when you interpret a principal component and you look at its loadings, and you can do that using the metabo-analyst, essentially you're looking at the weighted combination of all metabolites in the data set. So this is exactly what I was talking about in the two-dimensional case. I have, two metabolites, and my data vary like this. So you can easily see that there is a strong positive correlation, although on the plot on the right, there is a much stronger positive correlation. So here, by just using one principal component, there is still a lot of additional variability that I'm not capturing because the data still vary on the orthogonal dimension. So that means that potentially I may also want to use a second principal component to capture more variance in the data and therefore have a better representation. On this data set, there is no need essentially to use a second principal component because all the observations had the principal component direction, and essentially you can summarize the data by just looking at one variable. That's the beauty of it. That's why principal components I always like to think as a nice and clean way of summarizing your data and getting a global view. And you can see that here principal component analysis is more informative because there is higher correlations in the data. That's why all your data start getting closer to this line. Okay. So here is just some plots. I'm going to give you a lot of plots. And that's the question whether you need to do to illustrate one PC or to look at two PCs or three PCs. And what we see here, it's one view of the PUFA data where we have different days. We see, we see kind of some heterogeneity, but we also see kind of a grouping structure. Again, I told you that I don't want to use really principal component analysis to really cluster the data and identify groups, but in many cases, it provides a nice visual tool. So here is another view with three principal components. So here I'm using the entire panel, and we can see that the controls and the NFLDs do not separate that well. So that's where you start exploring your data. If you have a small target assay with 15 compounds, there are lots of other ways of visualizing and getting a feeling of the data. If you have 300 compounds, let alone 800 features, it's very difficult, to start looking at every metabolite, doing 800 box plots to really get a sense of what's going on. That's where principal component analysis becomes very useful because it starts providing these global insights, interesting patterns in the data. And for example, you know that using the entire panel of metabolites for the PUFA study, the two groups are not very nicely separated. So that means that in order sort of to find strong differences, you need to start drilling deeper. So this is PCA analysis for only two groups, the diabetics and the healthy, using all the compounds, all the named compounds. So remember that we have 264 compounds, and again, we don't have nothing jumps out. So here are two diagnostic plots that are provided in MetaboAnalysis and every software package of how we select the number of principal components, because this is very informative. And for example, when you review grants or you review papers, if people don't provide this information, make a comment and ask them to provide that information. So what this says, these are two different views of exactly the same information. So this says, so every data set on a standardized scale, its total variance, if you summed the variances of all the metabolites across all samples, you can standardize it to 1. That's exactly what it is. And then you ask the question, for every principal component, which is a direction of maximum variance, but you calculate, how much of the total variance it explains. So when you do the first weighted combination of your metabolites, how much of the variance you explain. This is related to this picture. Essentially, the first principal component explains most of the variance because there is very little variance outside this curve. Here, there is more variance left. You may care or you may not care to include a second principal component, but here, the variance explained by the first principal component, I would guess, is something like 95% of the total. So the less 5% is noise, you don't care. Here, probably something like 80%. So you may want to go a little bit further and do something, and maybe that's why you may want to do a two principal component analysis. Use the second principal component. So what this says is, for the SWAN data, the first principal component only explains 11% of the total variance. So there is a lot of patterns that happen if you only look at the first principal component. Unfortunately, when you bring the second principal component, we have only explained 20% of the total variance. And therefore, there is still, so when you look at the plot here, this plot has only captured 20% of the total variance in your data set. So that says that there might be a lot of other interesting patterns in the other 80% but is not captured on this plot. Again, you may care or may not care, but these are the mechanics. This plot is exactly the same. This is a cumulative variance. So the first one was at 11%, and then when you add the second one, you get at 20. And for example, if you wanted even to explain 50% of the total variance, here, you need to have about 12 principal components, which is fine, but you cannot visualize it unless you have very fancy visualization software, or virtual reality or immersive reality or whatever, the latest technology is. So that's why when people always like to put PCA plots in papers, this information of how much variance they explain is very, very important. There might be a lot of other patterns that are not captured by the plot. There is nothing wrong with what they put, but they need to provide that information because in this particular case, if suddenly I start jumping up and down and saying, oh, there are these great differences between this group and that group, I'm overinterpreting the results. Because the other 80% that I'm not capturing in this plot may completely negate this finding. So for example, if I brought the third principal component, suddenly all the data points may start coming together. So that's why that information is important. So the SWAN data set, with 2, even 3 principal components, we start getting a little bit more than 25. They're not that strongly correlated. So a good thing about the properties of the lipid classes that TM told us yesterday is that because the lipid classes, due to their biochemistry, are much more strongly correlated, when you do PCA analysis on the lipidomics platform, you get much stronger correlations, which is exactly the hallmark that you capture with principal component analysis. So even using 2 or 3 principal components, you explain much more of the variance, and these are much more representative plots regarding global patterns. Yes? My next slide. Yes. Absolutely. Absolutely. So that's where we start combining the material that we covered about testing in order. So what this plot tells me is that by using all the compounds, there is not enough correlation structure in the data. So what I'm doing here is I'm only using the differentially expressed compounds. Unfortunately, if you remember from yesterday, after we do FDR correction, we don't have that many significant differential compounds, but that's life. So you can see right now how the plot has changed. Once I go to the differentially expressed compounds, my first principal component captures 35% of the total variance, my second about 22. So the aggregate, by looking at this plot, and suddenly you see there is not a very clean separation between the diabetic and the healthy controls. But these data are much more correlated because essentially with few principal components, I explain a lot of the variance. I'm at 60%, and if I throw the third PC and I get a nice three-dimensional view, and in metabo analysis you can even rotate it and therefore get a much nicer view, essentially you have explained most of the variance. So following up on Ala's point, that's where these type of techniques that allow you to get a global view in the data coupled with differential analysis starts telling you, what are the patterns or other interesting patterns in the data, but at the same time you start reducing the number of compounds. But remember, from this perspective, what you are looking at is you are trying sort of to understand correlations and variances, variability. This is how the technique looks at. If you're asking a different question, that may not be the right technique. That's why I said, although in many cases I also use it to visualize whether the data have a nice cluster structure, this is not the technique to use to find clusters. So, yeah, so here, this was another data set. And so coming back to your question, principal component analysis, especially if it captures an adequate percentage of total variance, is a good technique to identify outline observations. So here, from this perspective, I'm explaining, or the data explain, the two principal components explain something like 52, 53% of the total variance, and these three observations jump out. So here was, in this particular case, we used the principal component analysis as a quality control type of visualization technique because I had two batches of data, the blue batch that was run on day 1, the red batch on day 2, and essentially you see that there were not very strong differences, but except for these three outliers. So in that case, then you need to get into normalization, but if, suppose that these 3 points were somewhere there, you didn't even need to even normalize. Essentially, you would go to a log2 scale that Farsad and Tanu mentioned yesterday, and you start your analysis. So this is another way of using sort of PCA, and the core uses PCA plots from that perspective as well, in order sort of to get a global view of whether there are strong batch effects, how much you need to normalize, and so on and so forth. But PCA is a good technique for identifying multivariate outliers. Because here, you're looking, these stand out when I use hundreds of compounds. So these are multivariate outliers from that perspective. But again, don't overinterpret. If this was explaining 5% of the total variance and this 3% of the total variance, and in order to capture a good chunk of total variance, I needed 50 principal components, then essentially you have no information. Then you cannot jump to the conclusion and say, oh, I have multivariate outliers. I need to apply a very strong normalization technique. So that's why this information is so useful, and a lot of people ignore it and overinterpret these plots. Okay. Yes.
Did you say the blue and the red dots, they are acceptable batch effect?
Yeah, I mean, there is a little bit of batch effect. Okay, don't get me wrong. But the point that I was trying to, maybe I didn't make it very clear, the thing that jumps out in this particular case is that I have 3 extreme outline samples, and therefore I need to do something with them. So, and in this particular case, this may be just an issue of the run, because here I'm just plotting the 2 different batches. Yes, there is still definitely a batch effect, because all the reds cluster to the left and all the blues cluster to the right, so probably I need to do a little bit of normalization. But one of my points was that PCA is a good technique to identify multivariate outliers. And identifying multivariate outliers is a very hard problem. So this is one solution. It's not the only solution, but other better solutions are technically very complicated. There is not good software. So this is another way of using principal component analysis. But never forget to look at this information. You first need to make sure that the plot captures enough information. So, sure.
One more question. So if you change, for example, the plot and plotted PC3 and PC4 together, you might see other type of outliers.
Sure, absolutely.
So then if you want to consider all the principal components to identify clearly one outlier that will be very different, then you need another kind of statistical analysis, right?
Yes, but that's where I'm relying on the fact that maybe with the first three, because the third principal component is going to capture mathematically less than 9%, at that point I start getting close to 60%. And then, the question is how significant those differences are. Unfortunately, we live in a three-dimensional world, and therefore visualizing 5 principal components, either you need very sophisticated software, or essentially, this software that essentially keeps rotating and giving you different views. And there are such packages out there, but most of them are not freely available. But you need to use more advanced visualization techniques, and then you can start looking into many more principal components by creating dynamically evolving views of your PCs. Okay. So, these are different ways of using PCs. TM showed us this plot, and he was using again for quality control, and and he could differentiate. And the good thing is that the point that he was making yesterday is that the test pool is somewhere in the middle of all his real samples, and that's always another comforting thing, because the test pool essentially has contributions from material from all the groups or from all the cell lines that he was looking at, and if the test pool was out there, that's worrisome. This is these are the plasma pools that the lab runs in order to figure out that every day is like any other day. But the test pool needs to be somewhere in the middle of your samples. We already talked about identifying outliers. So, okay, I'll skip this. Let me get to cluster analysis. Yes? Yeah, there is no watch, and I don't have a watch. Yeah, this is a good point to take in unless there are some questions before we take a break. Sure.
But I know you guys use the pooled samples as your control to kind of make sure that everything is stabilized. But how do you account for any degradation in your samples itself?
Maureen, that's an easy question for me.
Oh, I would say the best way to do that would be repeat injections of random samples, just to kind of look over the course of the run, whether, that sample 4, which is at the very beginning of the run, gives you the same signal at the end of the run, to see if that would be a biological degradation after you've normalized it based on your pools. So in other words, if you run your pools and you've normalized everything in between, and you have a repeat injection of that one later, then any difference you see is sample degradation or biological degradation. Right, because you've already corrected for that, because you already corrected it by using the pools to correct for the instrument drift. Does that make sense? Okay, so you're going to have pool 10 samples, pool 10 samples. So by the time you got to the end and you're at your 100th sample and you've run 10 pools, for all the samples in between, if you say that your first one metabolite's 100,000 in the pool at the beginning and it's 80,000 in the pool at the end, then you're going to correct all the samples in between by some small percentage to make up that total variance of 20% over the course of that time. And then, so if there's any degradation, so then if you repeat an injection of your actual sample, then that would be sample degradation that went on.
Use this opportunity just to mention something else. So for example, if you had a relatively small study, you do these test pools and all the things that Maureen explained, and you run them, and there are all these ways to sort of detect that everything went fine. Right now, let's think of another setting where your study has 500 samples, or even to make it more fun, 10,000 samples. These studies are coming up. So in that case, you need to think very carefully, and both the core, but also you as the investigator, you need to think very, very carefully, because there is no way that you're going to create a test pool of 10,000, correct? So that means that you're going to have different test pools for different batches of your real samples. And in that case, the moment you start going to large studies, you definitely need to work with an expert that understands all these experimental design issues and also how to design the run order. It's not a simple matter, okay, here are my 80 samples, create the test pools. This is very standard technology. But for large studies, talk to an expert even before you ship your samples. On that note, coffee break.